Welcome to another episode of the Corrosion Journal interview series. My name is Sammy Miles, and I'm the managing editor-in-chief of Corrosion Journal, AMP's peer-reviewed scientific journal. I'm excited to welcome the authors of a recent invited critical review on pit-to-crack transitions of metallic structures, Ryan Katona, Aaron Karras, and Rebecca Schaller from Sandia National Laboratories. Thanks for joining me today.
Thanks, Sammy.
Now, before we start discussing your review, can you share a little about yourself?
Sure. Thanks, Sammy. First, this is Rebecca Schaller. I just want to say thanks for having us here today. So a little bit on my background in corrosion, basically. I started at UVA with my PhD there in materials science. My advisor was Professor John Scully. After that, I came to Sandia as a postdoc, and I was working with Eric Schindelholtz in the Materials Reliability Group. I went up to the University of British Columbia for a little while as an assistant professor working in the materials engineering department there. And then I recently came back to Sandia, well, not so recently, I guess it was more like about almost 4 years now. And I'm now a staff member in the Materials Reliability Department. The primary focus of a lot of my work is working with the spent fuel waste storage and transportation program, looking at the potential for chloride-induced stress corrosion cracking to occur on dry storage canisters.
So I'll introduce myself next. My name is Ryan Katona. I'm currently a postdoctoral research at Sandia National Laboratories, being advised by Rebecca Schaller. A little bit about my path to science. I started out obtaining my bachelor's of science in physics and mathematics from the University of Lynchburg in Virginia. I then went to UVA, where I obtained my PhD in materials science and engineering, being advised by Professor Robert Kelly. During that time, I was fortunate enough to also obtain an internship at Sandia, working under Eric Schindelholtz as well as Rebecca Schaller. My overall dissertation topic was on localized corrosion and stress corrosion cracking in atmospheric environments. After my internship and after graduating with my PhD, I transitioned to a postdoc, again working under Rebecca Schaller. And current efforts again support the research Rebecca described, but also including modeling aspects of different material systems, as well as running our stress corrosion cracking lab here at Sandia.
And I'm Aaron Karras. I got my start as a electrical engineering student at Colorado State University. And during that time, I was an undergrad intern at Sandia, where I developed a love for materials and materials engineering. So that inspired me to pursue my graduate studies at Arizona State University, where I studied material science and engineering under Dr. Carl Saradsky. I then went on to be a postdoc under Dr. Rebecca Schaller and Dr. Michael Melia, and I recently transitioned to a staff position at Sandia as a material scientist.
That's great. Thank you for sharing. And I guess kind of related to your background, what really got y'all interested in the topic of your review paper that we're going to be discussing here in a bit?
Yeah, so I think a lot of it stems from, as we all mentioned, we work in the spent fuel waste storage and transportation program. And as a part of this program, both the DOE and NRC identified a few years, maybe about 10 years ago, they did a gap analysis report. And they identified stress corrosion cracking as one of the potential gaps in long-term storage of spent nuclear fuel. So our research at Sandia focuses a lot on if stress corrosion cracking were to occur, predicting when and where that might occur across these canisters. One component of stress corrosion cracking is obviously the initiation of a crack. And that could occur due to a pit to crack transition. Essentially, a corrosion defect occurs on the surface. A corrosion defect might exist in an existing stress field. And if those stresses are high enough, that could cause stresses to concentrate where that defect is and transition to a crack. So it could be a crack initiation point there. So we wanted to look through, before we started studying it, we wanted to kind of mine the literature and see what was out there in terms of research on pit to crack transitions or stress corrosion cracking initiation. So we collected a lot of information on this, but we found that there were still many areas for potential growth in this field or areas for potential study. So a lot of this information, we also found that it wasn't just pertinent to dry storage canisters or even just austenitic stainless steel, but that could apply to a lot of other industries such as aerospace or infrastructure, et cetera. So we thought it was a review that might be of broad interest to the community. So we kind of wanted to summarize all this into something that could put it out there, not just what's out there, but what might impact future study.
Excellent. I mean, that makes a lot of sense for a good starting point. For those listeners who haven't read your article yet, it's called A Review of the Governing Factors in Pit to Crack Transitions of Metallic Structures. And it just came out in our January issue of the journal. Would y'all be able to provide a brief overview of some of the topics covered? I know you kind of addressed that a little in what got you interested in it, but kind of what's the scope of your paper, and what can they learn more about when they read it?
Yeah, so there is a lot of work that has been done on this transition point because it's been something that's been studied for the last 40 to 50 years, is this pit to crack transition. And when we started out, we really wanted to make it a materials agnostic review, but the bulk of the research is on steels and aluminum alloys. So that was sort of where we ended up honing it down and focusing in on that. We were trying to distill it down to the things that we felt were most important, or maybe the things that had been most focused on over the history. And by virtue of that, a lot of the work that we talk about in the paper focuses on fatigue, which makes sense when you consider how this idea of the pit to crack transition point started. We talk a little bit about some of the historical takes on this transition, like the Kitagawa-Takahashi approach, where you're given a threshold stress range that is dependent on the flaw size. And if the flaw size and the threshold stress are exceeded, then the material is expected to fail. Another common historical approach is the Kondo approach, where you consider the fatigue crack growth rate to be at competition with the pit growth. And then there's going to be a point where the stress concentration is great enough that your fatigue crack growth rate will overtake that pit growth rate. And then that would be considered your pit to crack transition. The first sort of topic that we try to delve into is really focused more on the pit and the aspects of the pit that people have explored as being factors through history. So we start out looking at the impact of pit depth on this point of pit to crack transition, and then we add a little bit more complexity and delve into the research that was done on things like pit aspect ratio and whether or not your pits have like sharp features or asperities, which can arise out of things like your microstructure or your corrosion environment. And we look at the microstructure and how that plays a role in your pit to crack transition, as well as how close one pit is to another, so your pit density. And then we move into, okay, now we've looked at the pit, what about the load, right? How are we loading our sample to get this cracking? And we go through literature that looks at how the magnitude of the load influences that transition and how the frequency of that load in the case of the fatigue affects that. And it will also impact where your stress is or strain is concentrated within the pit. And we look a little bit at the impacts of the residual stress also on this pit to crack transition. And like I said, there's a lot of research that's been done out there, but we also wanted to touch on other impacts of the material and the microstructure. So we look at how the microstructure of a material, things like constituent particles, how that could cause preferential pitting at certain locations, and that then they could be more or less prone to fatigue cracking even separate from corrosion, and how that could possibly confound your variables and what you're looking at. The microstructure itself is going to have an impact on the pit in terms of potentially creating sharp features. We look a little bit at that. And we also spend a little bit of time talking about other factors that may or may not be well covered in literature, things like the impact of hydrogen embrittlement on this transition point, how your materials are processed, and if that affects your transition point, as well as the corrosion methods and the metallurgical differences that are used in different studies and how then comparing those different studies may be more difficult. And we also touch just briefly on how the metallurgical differences of additively manufactured metals could further complicate this research and make it difficult to tell really what's going on and what the most important factors are.
Great. Thank you for giving an overview. And with that, you've touched on a whole bunch of different areas. So what are a few key takeaways? So when you were going through the literature and going through each of these different sections, were there a few highlights that you could share with our listeners?
Yeah, one of the things that you find in literature is that increasing your pit depth definitely increases that pit's ability to concentrate the stress. But it's likely not the sole governing factor of when you're going to transition from a pit to a crack. And even once you add that additional layer of complexity by considering the aspect ratio of the pit, that's not even really sufficient to define crack initiation. But the literature does show that the concentration of the stress and strain by the pit are very important factors for this fatigue cracking. We also see that, probably predictably, as you increase your load, you're going to decrease the amount of time it takes in terms of the number of cycles when you're talking about fatigue to crack initiation. But the location of that crack can change when you change your load. And importantly, the location of the strain concentration within that pit can also change as you change different aspects of your loading. Overall, no single material or microstructural property or even property of the pit is going to exhibit a clear enough correlation with the initiation of cracking that you can distill it down to just one variable. One thing of particular note is that in a lot of the research, the corrosive environment gets removed when you're doing the loading of your sample. And therefore, when your cracking is occurring, you don't have that corrosive environment. And experts have already agreed that for initiation under static loading conditions, that environment has to be present in the pit. But this is an area that hasn't necessarily been as explored for fatigue conditions. So that's definitely an area of interest moving forward and something to consider when you look at the research that's out there.
Now, is the environment changed for the ease of conducting the research itself, or is that just so that they can try to distill it down to a single, variable to look at what's changing? If that made any sense.
No, it does. It does. And the truthful answer is in some cases it's both, right? In some cases you're using your corrosion methods to control aspects of your pit, or because you want to look at your pit before you're able to apply your load. Because if you're corroding while you're cracking, there's a potential that your pit is going to be changing shape. So there's a lot of different reasons. It can just be for ease. It can also be because you want to look at the pit more carefully before you start your cracking.
That makes sense. And this might not be an easy answer. Is there a way to actually monitor it in situ as you go? If you didn't remove it, like if it's easier to for example, you change that environment, is it something where you can conduct a study and actually see what's happening, or does that get really complicated?
I think that gets really complicated, and it seems like there's a lot of research that's moving towards that direction. But particularly when you're talking about working with something that's corroding, you have to be careful about what kind of instrumentation and how close you can put it. And
right.
The time scales of those techniques may or may not be conducive to looking at fracture and pit growth on the scale of time you're interested in.
Right. No, that completely makes sense. And one thing that I did want to talk to y'all about, in the review, y'all touch on a few areas that still need additional exploration. For example, in modeling, can y'all share a few examples? I know you mentioned one earlier on that we just talked about on future areas to investigate, but what are some of the others?
Absolutely. And modeling was one of the aspects that we highlighted through this review. So first and foremost, there are a lot of good models out there, some that are validated, some that are multi-physics in nature, so that they are accounting for both the mechanics side of things as well as the corrosion side of things. But we just think that there's computational advances that could potentially help push this further down the road and help account for this really complex modeling phenomenon. And so first in the review, we highlighted what was just general corrosion modeling. Corrosion modeling can be a very tricky thing to model in general. There's a bunch of underlying equations that are very complex that make it very computationally expensive, or it just takes a super long time to run these models. And so accounting for these with enhanced computational efforts or computational powers that we now have could help out in this pit to crack transition. Another thing that we noticed in a lot of corrosion modeling is that they're performed under driven conditions. And so what I mean by that is that they either apply a potential apply a given current to the entire system. And it's fairly easy to validate that in a lab, but when you go to a real world setting, it's potentially not the same conditions that you're doing. So you validated a model under driven experiments, under driven conditions, but you're not always able to extrapolate those conditions to an undriven experiment that you could see in real world conditions. Another thing with corrosion modeling is that the species that are present can play a large role in that process. And so chloride and pH are known to be bad actors for localized corrosion reactions. And so typically models either track one or the other. It's a little bit hard to track all things that are going on in these localized corrosion features. But again, with the advances in computational power, it may be possible to create these newer models in general. Another thing that we've seen a lot is that models are done in two-dimensional. It just makes it so much easier to do these models. You have a bunch of different aspects that or a bunch of different locations that you're not tracking when you're in 2D scenarios. This problem is an inherent 3D problem in general, but it just gets way more complex. You need a much more memory space, computing power in order to do this. But in order to capture the correct stress states, in order to capture the correct pitting morphologies, we do need to kind of push the envelope of 3D electrochemical and stress modeling into these complex models to describe this phenomenon.
With that, are y'all working on, are any of these problems that y'all are looking to tackle, some of those, how to do some of those maybe 3D models or anything else? Or are you aware of other people who are starting to do research in this field, or that area, I should say?
Yeah, we're working currently on it at Sandia and various different avenues, maybe not directly for the pit to crack transition. At the end of last year, we published a paper looking at electrochemical conditions in a propagating crack. So it's after it's transitioned from a corrosion feature to a stress corrosion crack. And so we've highlighted some key important variables for that modeling scenario. We've subsequently started to transition that to a 3D model. It just takes a very, very long time, as I mentioned, in terms of computational power. But we are starting to develop 3D models for corrosion-related phenomenon, especially in these highly occluded, very small environments that we're interested in.
And are y'all hoping that other researchers pick up on this as well to, they read your review and they go, oh, I didn't realize there was a gap in, X, Y, Z. Let's explore this. Is that one of the long-term goals other than y'all's research itself?
Most definitely. And how we wrote it from a material agnostic standpoint, or just trying to cover all materials, that's one of the goals that we were doing. Even one thing that's highlighted in the review, if we made one model for just the pit to crack transition itself, you could even divide that model into just a pitting model or to just a cracking model. And so you can kind of start to develop one model and parse it out to other material systems or other degradation modes that are potentially happening in your material as well.
Excellent. Now, did y'all come across anything in the literature that surprised you when you were putting together the review? So when you were going back through some of the old studies, was there anything that y'all didn't know, for example?
I think, first to start out, there's a lot of good work out there. And there's over 300 references that we have in this review. Trying to summarize that all into one and highlight all the important works is definitely an important part of this. But just a general lack of consensus was kind of surprising to us. That potentially also one detrimental aspect in one material system wasn't transferable to another, or potentially the fact that we transfer principles from one loading mode to another without investigating that phenomenon was something that we found interesting in literature. Another aspect of this is that it is a very, what we like to call a multi-physics problem. And so it takes chemistry, it takes electrochemistry and fracture mechanics kind of to understand this very big problem for our community. And so typically you have potentially a fracture mechanics coming into an electrochemistry problem, and a lot of us have a background in electrochemistry, potentially going into a fracture-related phenomenon. And so we kind of just need that interdisciplinary nature and collaboration to kind of push the ball further down the field in general. Another thing that Aaron had touched on was just how these are tested. Stress corrosion cracking, first off, has very limited amounts of standards in order to test this. And the pit to crack transition, most likely, I think there may be one potential published study out there or standard out there to test this. But it's also very limited in terms of standardizing this across the board. How actually do you test this? And Aaron had mentioned something that I'll kind of reiterate a little bit more, is that it's almost a catch-22 phenomenon. You want really good characterization of your feature to know potentially where a crack can nucleate, but you do remove that corrosive environment. If you don't remove that corrosive environment and you allow for potential crack to nucleate from that, if you don't remove it right away, your corrosion feature could change and your potential nucleating feature could be gone by the time that you look at it. Another aspect of this that we kind of highlighted in the review was the influence of hydrogen that could play a role in the pit to crack transition. So it's possible that hydrogen from electrochemical reactions could embrittle your corroding front or the near surface where a crack can nucleate. If you remove that from the environment, hydrogen, depending on how long characterization takes or what environment you store it in, your hydrogen could actually come out of the material, or just you could have massive changes in your near surface material properties throughout this entire process. And since it's a surface sensitive related phenomenon, keeping those variables and tracking those variables is very hard, but is essentially necessary to understand the mechanisms of this complex problem. You had also asked a question about, can we measure these local environments, or how do you get at looking at this? That's not widely done, but it has been done for stress corrosion cracking scenarios. And so I think a lot of this in situ measurements with crack growth rates actually started with Kevin Cooper and my former advisor, Dr. Rob Kelly at the University of Virginia. We've started doing that here at Sandia for stress corrosion cracking related problems. And we know of some work at Ohio State that's being done as well at measuring these localized environments at crack tip related geometries. But again, cracks are potentially easier to monitor than just a corrosion feature that could be on the size of a few microns.
Right, and thank you for adding that in and looping back to that question. Before we wrap up, is there anything else y'all would like to add or touch on? I know there's one thing that I didn't mention earlier, and that your article is open access permanently. So if there's any readers who would like to go back and look at it, you don't have to have a subscription to access it. Just go to Corrosion Journal's website to our January issue, and we can include a link to the article on the in the podcast description itself. But with that, sorry, I forgot to mention that earlier, but is there anything else y'all would like to add today?
No, I think we're good on our side, Sammy. I mean, we'd be happy to answer any questions, but from any listeners in the future, but I think we're good on our end.
With that, what would be the best way for our listeners to reach y'all if they had any questions or follow up?
In terms of the review article, they can ask questions to my email. That's RN as in Michael, KATON as in Nancy @sandia.gov.
Perfect.
And Sammy, I'd be happy to help answer any questions on the review article, or also on just the program at Sandia more in general. And my email addresses are schall@sandia.gov.
Perfect. And we will post those on our website as well, so that if people can easily contact y'all if they have questions either on the article or on the program at Sandia. And thank y'all for joining me again. And with that, I'm Sammy Miles. I'm here with Ryan, Aaron, and Rebecca. And thank you for listening to another episode of Corrosion's interview series. If you want to learn more about the journal, make sure to visit corrosionjournal.org. You can subscribe to AMP Podcast if you haven't already on Apple, Google, Spotify, and all the major distributors. You can find all episodes of AMP Podcast on amp.org. That is ampp.org. We'll be back soon with another episode. Thanks for listening.